Hey folks, this is Captain Jones here to talk to you about the HackCPU. This is a neat, kind of somewhat hypothetical computer that will hopefully build out our understanding of, just a different way to build a computer. This is actually taken from a book here called The Elements of Computing Systems. This is a super cool book. The authors, tried to tackle the lofty goal of effectively showing someone how a computer works, all the way from, in chapter 1 they talk about basic logic gates, the stuff you learned about in E360. In the first half of the book, they build a computer, which is the one we're going to look at today, and in the second half of the book, they sort of work towards building a full operating system for this computer, so that the student can understand the whole spectrum of how these computers work. From hardware to software. So really neat. It's also got a Coursera course, which if you're interested later, you can kind of like sign up for and follow along. And there's a link down at the bottom to the kind of home webpage, nantotetris.org, which is the affectionate term for this book here, meaning, kind of colloquially, that you go from NAND gates all the way up to being able to build a computer that can run something like Tetris. Okay, so our objectives today are to discuss the architecture and the organization of this computer called the HackCPU. And then additionally, I'm going to take a couple of minutes to kind of compare the HackCPU with the little man computer and kind of put them side by side and show the various ways in which they're similar and different. So, okay, let's get started with memory. So to start with, you can see a graphic kind of down here of the HackCPU. So we've got our computer right here in the middle. And the first thing to note is that this is a Harvard architecture. So in the HackCPU, we have separate memories for instructions and data. You can kind of see that here where my instructions are fed into the processing unit. The processing unit is able to access data memory, which is separate. Both of these memory spaces in the HackCPU are 2 to the 16th spaces tall. So that means they can store, like you can see on the right here, 65,000 data values effectively, and each one is 16 bits wide. So separate instructions and data, each one 2 to the 16th locations tall. Each space is considered one word, so that's kind of like the computer term for one chunk of bits that the computer operates on. And memory is said to be word addressable. So you can see here kind of on the right that if we increment a memory address by 1, that means we go from one word or one group of 16 bits to the next one. This is a kind of a simplified picture of the CPU that's in the Hack computer. And so what I want to draw your attention to here at the bottom is my ALU. So that's my arithmetic and logic unit. This is the thing that's doing all the hard math stuff. And effectively, I've got 2 registers in my CPU, A/M and D. And you can almost think of this as sort of like D is sort of like a data register. It's just a plain old register. The A/M register is kind of unique. It could potentially hold a piece of data. So you can see here that if I want, I could sort of send the value in this register directly through this multiplexer into the ALU. So I could potentially, like add 2 values in A and D or do something else. Alternatively, I could treat the value in this register as if it were an address in data memory. And I could send the value in my data memory that's at that address through my multiplexer into my ALU. So that's kind of where it gets the name A/M. A is sort of like, the value or potentially an address. M is referring to the actual memory location that's pointed to by that value. And so I can use either one. So that's a really versatile feature. And you'll notice here that the output of the ALU could be sent to either the D register or the A/M register, or even back into the data memory. And where it gets stored here again is whatever address is specified in this register. In the HackCPU, there are effectively 2 types of instructions. Each one is 16 bits wide. Okay, so 16 bits to specify our instructions. The first one is what we call an A-type instruction, and it's given that name because when bit 15 is 0, the HackCPU treats the rest of the bits 14 through 0, as if it were an unsigned value, 15-bit value. That value gets 0 extended and stored into the A register. So the only thing this instruction does is place a value into the A register. The other instruction that's available to us in the HackCPU is called a C-type instruction, which is marked by bit 15 being a 1. This is like a Swiss Army knife type instruction. So we'll take the next couple slides to kind of pick apart what each of these fields mean. Bits 14 and 13 aren't used, so by convention they're just set to 1. Bit 12 here is called A because this is the bit that sort of determines, or it sort of sets this multiplexer and determines whether the value that's sent to the ALU is the value in the A register directly, or the value in data memory whose address is in the A/M register. So so the A bit here kind of controls whether or not I've got my A register or my data memory that's going to my ALU. Next is my opcode. I've got 6 bits here for my opcode, so I got a lot of room to make a whole bunch of different stuff. You can see here kind of really a partial snapshot of everything that this ALU can do. And so I'll direct your attention first here to the upper left. You can see that I've got my A bit here that's controlling, again, whether or not I'm kind of operating on the A or the M register, and then my 6 opcodes, or sorry, 6 bits of my opcode. And so right now this kind of looks like gobbledygook, but so I just want you to see that if I've got 6 bits, effectively I've got something like 64 potentially different operations. And as opposed to the little man computer, I can do a bunch of stuff with that. Right, you can see here on the right hand side that I can configure my ALU to, regardless of the operands, output a 0 or output a -1. Or I can, negate the D register or the A register. I can add 1 to the D register. I can add 1 to the A register. I can do lots of neat things with these values. And the way the HackCPU does this is actually super cool. So this is a picture of the ALU inside the HackCPU. And you can see I've got my 2 inputs. This would be my D register. X would be my D register. And what I've labeled Y down here would be my A/M register. And so in both cases, my 2 inputs, I have a bit that controls whether or not the actual register goes through, or I just use a 0 value. So ZX means sort of 0X, ZY means like 0Y. After that, again, in each case, I have another bit, so 2 bits total, that let me choose whether or not the value that comes out of this multiplexer is negated or not. So I got a NX for like a negate X and NY for like a negate Y. The output of both those muxes are ANDed and they are added together. So I do an ANDing and an adding. And then those two are sent to this multiplexer, f of x here, that controls whether or not I take the result of the AND gate if it's 0 or the adder if it's 1. And then lastly, I have the option of, if I want to, negating my output. So I can pass the output of this multiplexer either straight through to my output, or I can negate it. And so right at the bat, right, I can add stuff, I can AND stuff. But when I start to leverage these other kind of zeros, knots, negates, I can do some lots more stuff. So let me demonstrate that kind of real quick if I could. This is a Logisim model of the ALU, which is available to you if you go to the additional resources section. And so I'll demonstrate really just one thing right here to show kind of how we might use this to build some really neat stuff. And so I'll show you, with that AND gate here, if you recall De Morgan's theorem, right? De Morgan's theorem sort of showed us how to sort of turn an AND gate into potentially an OR gate if we negate some stuff on the inputs and the outputs. So if it's not familiar, refresh your memory. De Morgan's theorem says that the ANDing of something, if we throw a NOT gate on both inputs and a NOT gate on the output, is effectively the same thing as the logical OR. So let me set this up here. I'm going to turn on my 2 negations, and then I'm going to negate the output. And what this output here should show now is the logical OR of these 2 inputs. And so if I test that here, if I put a 1 here, I get a 1 on my output. If I put a 1 in the next position over in my next register, that's ORed together on my output. If I turn this last bit on, it doesn't really do anything because I'm just ORing it with this bit, which is already set to 1. So you can see from this that with this sort of configuration of input bits or of opcode bits, I can configure the ALU to do a logical OR. And in fact, there's lots of neat stuff that it can do. Under the additional resources section, I compiled all the kind of the different useful opcodes that you might want the HackCPU to do, and you can see. Let's see, where is it? You know, I'm actually not seeing it on this list, the logical ORing. Anyway, this is straight from Wikipedia. So actually, this may not even be a complete list, but you can see here that you know, if we configure our opcode bits in certain ways, we can get these outputs. So anyway, so that's a pretty neat kind of like really elegant solution. Okay, so then so that's the opcode. Let's look at these last two fields now: destination and jump. All right, destination. These 3 bits control where the result of the ALU operation is placed. So recall that if I go all the way back to my diagram here, the output of my ALU could go to any of the D register, the A register, or memory. And so it is these 3 bits, the destination, that control that. And effectively, you could think of this like D2 here, sort of like, you know, if it's a 1, then it means put something in the A register. D1 effectively says put something in the D register. D0 says put something in memory. So I could sort of turn off and on, you know, any of these 3 registers in just about any combination to be where I want to store that result. And then lastly, I've got these jump bits. So J2, J1, J0 are the last 3 bits in that C-type instruction, and these control whether or not the HackCPU branches to a new location or not. You can see here that, you know, based on these 3 bits, I can either do no branch, I can set up various inequalities based on the output of the ALU. And so effectively what these do are say, you know, when this instruction is evaluated, if, for instance, you know, J2, J1, and J0 are in this pattern, 0, 1, 0. What that means is, you know, after the ALU's finished computing something, if the output equals 0, then the HackCPU will execute a jump. And it's sort of hard-coded to be that the location, the new jump location is whatever value is stored in the A register. So typically what you would do is sort of, you know, you put your destination where you would potentially jump in the A register, and then, you know, if you need to compute something in the ALU that doesn't use the A register, and configure these jump bits to jump to that new location if the inequality is set. Okay, so let's take a look at how we might put these instructions together to do something really simple like add 2 numbers. Let's say we wanted to add the values 5 and 4 together. So step 1 is going to be to load the value 5 into our computer. So what we'll do is we'll use the A-type instruction for that. That starts with a 0 bit, and then I have a 101 binary 5. And so when this instruction executes, the A register will have the value 5. I need to load another I need to load another value into that register, so I've got to put the value in the A register somewhere else. So what I'm going to do is move that number to my D register. So I'm going to use the C-type instruction for that. I'm going to configure A to be 0 because I want to use the actual value that's in this register. I'm going to use the opcode 110000, and if you look at that reference, you'll notice that means that tells the ALU just sort of pass through whatever values in the A register. And I'm going to configure my destination to be just the D register, so that the value in A goes through, nothing happens to it in the ALU, it passes all the way through, and it gets stored in the D register. I'm not jumping, so these bits are all 0. Okay, now I can load my second number into the A register, so I use another A-type instruction. Let's say I want to load the value 4, so this is what that would look like. Okay, so now I've got the value 5 in my D register, I've got the value 4 in my A register. Now I can actually perform my addition. So I'm going to add those 2 together. I'm going to use the C-type instruction for that. I'm going to choose this opcode, which is the equivalent of A plus D. And I'm going to put that value, let's say I'm going to put it back in the D register. So I'm going to overwrite this D register with the value of the addition. Again, no jump, so 3 zeros there. And to make this a little more interesting, let's say I'm gonna store that value into memory. Let's say I'm gonna store it in memory location 2. So what I need to do first is load the address into the A register, which is where I want to store this value. So I'll use the A-type instruction to put the value 2 into the A register. And now I can issue one last C-type instruction to store the D register into the spot in memory whose address is in the A register. So I'm going to choose this opcode, which if you look at the list is just passing the D register straight through the ALU. I'm going to set M to be my destination. So, so that value D is going to go through my ALU. It's going to get stored in memory at the location specified in my A register, which is the value 2. So memory location 2 gets the value of my addition, and again my jumps are 0, so because I'm not branching. So this is what it might look like to do something simple like add 2 numbers in the HackCPU. Okay, before we close out, let's ask really quick, how does this computer kind of compare to the little man computer? What ways are they similar and what ways are they different? So you can see here I've got kind of two graphics depicting the sort of block diagrams for these two things. And just looking at these, we might be able to pull out a couple of ways in which they are kind of similar and different. The first thing that I sort of identify when I think about these two is the fact that they got slightly different architectural models. So the little man computer is a true von Neumann computer, right? I've got 100 mailboxes that include both instructions and data. However, the HackCPU is a Harvard architecture. I've got that data memory here that I can operate on. I've also got the instruction memory that's separate from that. So they got different architectural models. Speaking of the memory, they've got totally different address spaces, right? The little man computer has 100 words or 100 memory spaces that it can use. The HackCPU has way more, right? I've got over 65,000 memory spaces, not only for my instructions, but also for my data. So you can imagine that the HackCPU already is, on that one feature is starting to differentiate itself as a much more capable computer. Okay, looking at this, my next attention kind of goes to the registers. I noticed that in terms of how, what is the word size? What's the chunk of data that the computers operate on? Well, the little man computer is 3 decimal digits, and that was that was intentional to kind of make it easier to understand for folks that didn't quite get binary. The HackCPU, of course, though, has 16 bits. So each register is 16 bits wide. The ALU itself is 16 bits wide. That's the word size for that computer. Additionally, we might look at just the number of registers in each of these devices. So the little man computer has one, really, which is kind of the accumulator that's in the middle of this little calculator. The HackCPU has two registers. And, which isn't a ton more, but that already, looking at the instructions, that gives us a little bit more we can do. Next, we might look at the number of cycles per instruction, in which case these two computers have the same. They both execute one instruction on each clock cycle. And we'll look at computers in the future that have a different number than that. Next, we might look at the actual kind of format of the instructions for these two computers. And as I look at these two kind of sets of instructions, again, my eye first notices the fact that for the little man computer, I've got 10 instructions, pretty short list. For the HackCPU, I've got a ton more. I have here roughly 28, and I got that number because I was looking at here there are 26 opcodes just in this list from Wikipedia. So that's 26. I considered all the jumps to sort of be one type of kind of branching instruction, so that was 27, and then of course the A-type instruction to me was 28. Unless I'm missing it, we identified just like a little bit ago that one of the instructions not listed here is the logical ORing of the two registers. So maybe there's even a couple more instructions in the HackCPU than just 28. Next, my attention goes to inside those instructions. What are the number of operands? So that the little man computer has, two groups of instructions. Some that take 0 operands, these 3 at the bottom, and then a whole bunch that take just 1 operand. And in the HackCPU, I've got this is incorrect. I've got it correct in my table here, but not on the slide. We've got one instruction that takes a single operand, and then the C-type instruction I considered as taking 4 operands: the A, the opcode, the destination, and the jump. So then the C-type gives us a lot more versatility. All right, next I might ask myself, or my attention kind of goes to, can I do some sort of indirect addressing? So we'll talk in a future lesson about addressing modes. And what this means right now, you could kind of imagine that the little man computer, there's no way to encode in an instruction in the little man computer how to get some value whose address is at a location in a mailbox, right? So like if, let's say, the user was putting entering some values in the inbox, and my little man computer was storing those somewhere in memory. I have to kind of know as I'm programming it, what those mailbox values are if I'm going to add them, because I have to use a literal adder, mailbox number in here. I can't sort of, make an indirect reference to those memory locations. And in the HackCPU, I can absolutely, right? We saw that in this little A bit here that kind of controls whether the A register is used directly in a calculation or whether it has an address that's referring to somewhere in memory. If you did any of the extra exercises on the little man computer, you might have found that was kind of a difficult feature to get around, which the HackCPU gives us. All right, next, I might ask myself, is it possible for one of the operands that go to the ALU to be in memory? In this case, for both computers, the answer is yes. That's sort of, for the little man computer, that's kind of baked into each of these instructions. Each of these X's refers to a specific memory location where I'm getting a value that I'm operating on. The HackCPU also, based on this little A bit here, can pull something out of memory. That's not always the case, but for these two computers, we can operate directly on values in memory. And this table here, this summarizes exactly what we just saw over the last couple slides. Okay, so there's a lot going on comparing these two. Why the heck is this important? We'll look at this a little more closely in a future lesson on design trade-offs. But right now, I'll just leave you with, one thing I want you to take away are just that there are lots of different ways to build fully functional computers. So the little man computer, the HackCPU are both full Turing complete computers, but clearly, based on some different design choices, they have very different capabilities. And furthermore, those design choices that computer engineers make when they're sort of building these two things directly affect things that the users and the designers and the programmers care about, like what's the final performance, how fast can this computer run, and how quickly can it process an email or something like that. How much power does it use? What's the overall cost? How hard is it to design and program? So if you end up doing the design trade-offs lesson, we'll look at a little more closely how these things here, these features of these computers, affect things that we all care about in terms of a computer's performance and power usage and things like that. Okay, so to summarize, today we looked at the HackCPU, which is a hypothetical computer described in the book, The Elements of Computing Systems. You can see kind of an overall picture of that here. The CPU, in a very simplified form, looks like this diagram on the right, where I've got two registers going to my ALU, one of which could potentially be used to refer to a spot in memory. And the ALU was super cool, this little elegant thing here that you can see, which uses 6 bits to control, an adder and an AND gate to do a whole bunch of stuff. And we looked at the fact that this was a Harvard architecture, so I have memory sort of chunks of memory for both the instructions and the data, and in this computer, really just 2 types of instructions: the A type and the C type. And the C type is my Swiss Army knife, right? Because this opcode, and between the opcode and the destination and the jump, I can do a whole bunch of different stuff with this instruction. All right. The quote I'll leave you with today is brought to you by Theodore Roosevelt, who said, "Do what you can with what you have where you are." That's all I got, folks. I'll see you next time.